NIST National Institute of Standards and Technology, U.S. Department of Commerce, SP 330, NIST Special Publication 330, the International System of Units, SI. This is the logo of the SI. CD, candela, kilogram. I'll explain this later. 2019 edition. David B. Newell and E. Tisinga, editors. This publication is available free of charge at this link. Inside front cover, blank. NIST Special Publication 330, 2019 edition. The International System of Units, SI. United States version of the English text of the 9th edition, 2019 of the International Bureau of Weights and Measures publication, by Systeme International de Unités, SI, supersedes NIST Special Publication 330, 2008 edition. Editors David B. Newell, E. Tisinga. Physical Measurement Laboratory, National Institute of Standards and Technology, Gaithersburg, Maryland 20899. This publication is available free of charge from August 2019. Department of Commerce, United States of America, U.S. Department of Commerce, Wilbur L. Ross, Jr., Secretary, National Institute of Standards and Technology, Walter Copan, NIST Director and Undersecretary of Commerce for Standards and Technology. Certain commercial entities, equipment, or materials may be identified in this document in order to describe an experimental procedure or concept adequately. Such identification is not intended to imply recommendation or endorsement by the National Institute of Standards and Technology, nor is it intended to imply that the entities, materials, or equipment are necessarily the best available for the purpose. NIST National Institute of Standards and Technology Special Publication 330, National Institute Standards Technology Special Publication 330, 122 pages, August 2019, code in NSPUE2. This publication is available free of charge from the DOI link here. Forward. The International System of Units, universally abbreviated SI from the French. Le Système International des Unités is the modern metric system of measurement. The SI is the dominant measurement system used in science and international commerce. In recognition of this fact, Congress is designating the metric system of measurement as the preferred system of weights and measures for United States trade and commerce. The definitive international reference on the SI is a booklet prescribed by the International Bureau of Weights and Measures, BIPM, Bureau International des Poids et Mesures, and often referred to as the BIPM SI Brochure. Entitled Le Système International des Unités SI, the book is in French, followed by text in English. This 2019 edition of the National Institute of Standards and Technology NIST Special Publication SP 330 is the United States version of the English text of the 9th edition of the brochure, the most current, published in 2019. The 2019 edition of NIST SP 330 replaces its immediate predecessor, the 2008 edition, which was based on the 8th edition of the BIPM SI Brochure, published in 2006, updated in 2014. The Secretary of Commerce, acting through the Director of the NIST, is authorized by statute, Section 15 U.S.C. 272 under subsection 2 to develop, maintain, and retain custody of the national standards of measurement and provide the means and methods for making measurements consistent with those standards, and under subsection 9 to assure the compatibility of United States national measurement standards with those of other nations. Under this authority, the SI is interpreted or modified by the Director of NIST for use in the United States. The Secretary of Commerce, acting through the NIST Director, is designated to direct and coordinate efforts by federal departments and agencies to implement government metric usage in accordance with the Metric Conversion Act, U.S. 15 U.S.C. 205B, as amended by the Omnibus Trade and Competitiveness Act of 1988. Like its 2008 predecessor, the 2019 edition of NIST SP 330 conforms with the English text in the BIPM SI brochure, but contains a few minor differences to reflect the most recent interpretation of the SI for the United States by the Secretary of Commerce as published in the Federal Register. These differences include the following. The spelling of English words is in accordance with the United States Government Printing Office Style Manual, which follows Webster's Third New International Dictionary rather than the Oxford Dictionary. Thus, the spellings meter, liter, deca, and cesium are used rather than meter, liter, deca, and cesium as in the original BIPM English text. The name of the unit with symbol T defined according to 1 T equals 10 to the third kg is called metric ton rather than ton. Since the preferred unit symbol for the liter in the United States is a capital L, only capital L is given as the symbol for the liter. A number of editor's notes are added in order to indicate such differences where significant, except spelling differences, and to clarify the text. And very few minor editorial changes are made in order to Americanize some phrases. Because of the importance of the SI to science, technology, and commerce, and because NIST I coordinates the federal government policy on the conversion of the SI by federal agencies and on the use of the SI by U.S. industry. 2. Provides official U.S. representation of the various international bodies established by the Meteor Convention, see page 1. And 3. Is responsible for interpreting and modifying the SI for use in the United States. NIST provides a number of other sources of information on the SI in addition to NIST SP 330. This includes NIST Special Publication 811, Guide for the Use of the International System of Units by David B. Newell and E. Tasinga. NIST SP 330, NIST SP 811. The aforementioned Federal Register notice are the essential elements of the U.S. interpretation of the SI. Users of this NIST publication are encouraged to take advantage of the resources, useful links, and other information available on the BIPM, www.bipm.org, and the NIST metric program, www.nist.gov/metric websites. August 2019. David B. Newell, 8 Tasinga. Note from the BIPM and copyright and use of the English text. All the BIPM's works are internationally protected by copyright. This document has been drafted with permission obtained from the BIPM. The only official text is the French text of the original document created by the BIPM. To make its work more widely accessible, the International Committee for Weights and Measures, CIPM, has decided to publish an English version of its reports. Readers should note that the official record is always that of the French text. This must be used when an authoritative reference is required or when there is doubt about the interpretation of the text. The BIPM and the Meteor Convention. The International Bureau of Weights and Measures, BIPM, was set up by the Meteor Convention signed in Paris on 20 May 1875 by 17 states during the final session of the Diplomatic Conference of the Meteor. This convention was amended in 1921. The BIPM has its headquarters near Paris in the grounds 43520 square meters of the Pavillon des Bretelles Parc Saint Day Cloud, placed at its disposal by the French government. Its upkeep is financed jointly by the member states of the Meteor Convention. The task of the BIPM is to ensure worldwide unification of measurements. Its objectives are to represent the worldwide measurement community, aiming to maximize its uptake and impact, be a center for scientific and technical collaboration between member states, providing capabilities for international measurement comparisons on a shared cost basis, be the coordinator of the worldwide measurement system, ensuring it gives comparable and internationally accepted measurement results. The BIPM operates under the exclusive supervision of the International Committee for Weights and Measures, CIPM, which itself comes under the authority of the General Conference on Weights and Measures, CGPM, and reports to it on the work accomplished by the BIPM. Delegates from all member states attend the General Conference, which normally meets every 4 years. The function of these meetings is to discuss and initiate arrangements required to ensure the propagation and improvement of the International System of Units, SI, which is the modern form of the metric system, confirm the results of new fundamental methodological determinations and various scientific resolutions of international scope, take all major decisions concerning the finance, organization, and development of the BIPM. The CIPM has 18 members, each from a different state. At present, it meets every year. The officers of this committee present an annual report on the administrative and financial position of the BIPM to the governments, the member states, and the Meteor Convention. The principal task of the CIPM is to ensure worldwide uniformity and units of measurement. It does this by direct action or by submitting proposals to the CGPM. As of 20 May 2019, there were 59 member states: Argentina, Australia, Austria, Belgium, Brazil, Bulgaria, Canada, Chile, China, Colombia, Croatia, Czech Republic, Denmark, Egypt, Finland, France, Germany, Greece, Hungary, India, Indonesia, Iran, Islamic Republic of Iraq, Ireland, Israel, Italy, Japan, Kazakhstan, Kenya, Korea, Republic of Lithuania, Malaysia, Mexico, Montenegro, Netherlands, New Zealand, Norway, Pakistan, Poland, Portugal, Romania, Russia, Russian Federation, Saudi Arabia, Serbia, Singapore, Slovakia, Slovenia, South Africa, Spain, Sweden, Switzerland, Thailand, Tunisia, Turkey, Ukraine, United Arab Emirates, United Kingdom, United States of America, and Uruguay. 42 states and economies are associated to the General Conference: Albania, Azerbaijan, Bangladesh, Belarus, Bolivia, Bosnia and Herzegovina, Botswana, CARICOM, Chinese Taipei, Costa Rica, Cuba, Ecuador, Estonia, Ethiopia, Georgia, Ghana, Hong Kong and China, Jamaica, Kuwait, Latvia, Luxembourg, Malta, Mauritius, Moldova, Republic of Mongolia, Namibia, North Macedonia, Oman, Panama, Paraguay, Peru, Philippines, Qatar, Seychelles, Sri Lanka, Sudan, Syrian Arab Republic, Tanzania, United Republic of Vietnam, Zambia, and Zimbabwe. The activities of the BIPM, which in the beginning were limited to measurements of length of mass and meteorological studies in relation to these quantities, have been extended to standards of measurement of electricity, 1927, photometry and radiometry, 1937, ionizing radiation, 1960, timescales, 1988, and to chemistry, 2000. To this end, the original laboratories, built in 1876 to 1878, were enlarged in 1929. New buildings were constructed in 1963 to 1964 for the ionizing radiation laboratories, in 1984 for the laser work, and in 1988 for library and offices. In 2001, a new building for the workshop, offices, and meeting rooms was opened. Some 45 physicists and technicians work in the BIPM laboratories. They mainly conduct methodological research, international comparisons of realizations of units, and calibrations of standards. An annual director's report gives details of the work in progress. Following the extension of the work entrusted to the BIPM in 1927, the CIPM has set up bodies known as consultative committees, whose function is to provide it with information on matters that it refers to them for study and advice. These consultative committees, which may form temporary or permanent working groups to study special topics, are responsible for coordinating the international work carried out in their respective fields and for proposing recommendations to the CIPM concerning units. Consultative committees have common regulations. Document CIPM D01 Rules of Procedure for the consultative committees, CCs, created by the CIPM, CC working groups, and CC workshops. They meet at irregular intervals. The president of each consultative committee is designated by the CIPM and is normally a member of the CIPM. The members of the consultative committees are metrology laboratories and specialized institutes agreed by the CIPM, which send delegates of their choice. In addition, there are individual members appointed by the CIPM and a representative of the BIPM. Document CIPM D01 Rules of Procedure for the consultative committees, CCs, created by the CIPM, CC working groups, and CC workshops. At present, there are 10 such committees. The Consultative Committee for Electricity and Magnetism, CCM, new name given in 1997 to the Consultative Committee for Electricity, CC, set up in 1927. The Consultative Committee for Photometry and Radiometry, CCPR, new name given in 1971 to the Consultative Committee for Photometry, CCP, set up in 1933. Between 1930 and 1933, the CCE dealt with matters concerning photometry. The Consultative Committee for Thermometry, CCT, set up in 1937. The Consultative Committee for Length, CCL, new name given in 1997 to the Consultative Committee for the Definition of the Meter, CCDM, set up in 1952. Consultative Committee for Time and Frequency, CCTF, new name given in 1997 to the Consultative Committee for the Definition of the Second, CCDS, set up in 1956. Consultative Committee for Ionizing Radiation, CCRI, new name given in 1997 to the Consultative Committee for Standards of Ionizing Radiation, CCEMRI, set up in 1958. In 1969, this committee established 4 sections. Section 1, X and beta, X and gamma rays, electrons. Section 2, measurement of radionuclides. Section 3, neutron measurements. Section 4, alpha energy standards. In 1975, this last section was dissolved, and Section 2 was made responsible for its field of activity. The Consultative Committee for Units, CCU, set up in 1964. This committee replaced the Commission for the System of Units set up by the CIPM in 1954. The Consultative Committee for Mass-Related Quantities, CCM, set up in 1980. The Consultative Committee for Amount of Substance, Metrology and Chemistry and Biology, CQM, set up in 1993. The Consultative Committee for Acoustics, Ultrasound, and Vibration, CCAUV, set up in 1999. The proceedings of the General Conference and the CIPM are published by the BIPM in the following series: Report of the Meeting of the General Conference on Weights and Measures, Report of the Meeting of the International Committee for Weights and Measures. The CIPM decided in 2003 that the reports of the meetings of the consultative committees should no longer be printed. They will be placed on the BIPM website in their original language. The BIPM also publishes monographs on special metrological subjects, and under the title The International System of Units, a brochure periodically updated, in which are collected all the decisions and recommendations concerning units. The collection of the Travaux et Memoires des Bureaux Internationaux des Poids et Mesures, 22 volumes, published between 1881 and 1966, and Recueil des Travaux des Bureaux Internationaux, 11 volumes, published between 1966 and 1988, seized by a decision of the CIPM. The scientific work of the BIPM is published in the open scientific literature. Since 1965, Metrologia, an international journal published under the auspices of the CIPM, has printed articles dealing with scientific metrology, improvements in measurement, improvements in methods of measurement, work on standards and units, as well as reports concerning the activities, decisions, and recommendations of the various bodies created under the Meter Convention. This page intentionally left blank. Table of contents, preface to the 9th edition. Introduction, the SI and the defining constants, motivation for the use of defining constants to define the SI, implementation of the SI, the International System of Units, defining the unit of a quantity, definition of the SI, definitions of the SI units, base units, practical realization of SI units, dimensions of quantities, derived units, units for quantities that describe biological and physiological effects, SI units in the framework of the general theory of relativity, decimal multiples and submultiples of SI units, non-SI units that are accepted for use within the non-SI units that are accepted for use with the SI, writing unit names and symbols, writing unit symbols and names and expressing the values of quantities, the use of unit symbols and names, unit symbols, unit names, rules and style conventions for expressing values of quantities, numerical value of a quantity and the use of quantity calculus, quantity symbols and unit symbols, formatting the value of a quantity, formatting numbers in the decimal marker, expressing the measurement uncertainty in the value of a quantity, multiplying or dividing quantity symbols, the values of quantities or numbers, stating quantity values being pure numbers, plane angles, solid angles, and phase angles. Appendix 1, decisions of the CGPM and the CIPM. Appendix 2, practical realization of the definitions of some important units. Appendix 3, units for photochemical and photobiological quantities. Appendix 4, historical notes on the development of the International System of Units and its base units. Part 1, the historical development of the realization of SI units. Part 2, the historical development of the international system. Part 3, historical perspective on the base units. List of acronyms used in the present volume. Index, list of tables. Table 1, the 7 defining constants of the SI and the 7 corresponding units they define. Table 2, SI base units. Table 3, base quantities and dimensions used in the SI. Table 4, the 22 SI units with special names and symbols. Table 5, examples of coherent derived units in the SI expressed in terms of base units. Table 6, examples of SI coherent derived units whose names and symbols include SI coherent derived units with special names and symbols. Table 7, SI prefixes. Table 8, non-SI units accepted for use with the SI units. Preface in the 9th edition. The International System of Units, the SI, has been used around the world as the preferred system of units, the basic language of science, technology, industry, and trade since it was established in 1960 by a resolution at the 11th meeting of the Conference General des Poids that measures the CGPM, known in English as the General Conference on Weights and Measures. This brochure is published by the Bureau International des Poids that measures the BIPM, known in English as the International Bureau of Weights and Measures, to promote and explain the SI. It lists the most significant resolutions of the CGPM and decisions of the Comité International des Poids that measures the CIPM, known in English as the International Committee on Weights and Measures, that concern the metric system going back to the first meeting of the CGPM in 1889. The SI has always been a practical and dynamic system that has evolved to exploit the latest scientific and technological developments. In particular, the tremendous advances in atomic physics and quantum metrology made over the last 50 years have enabled the definitions of the second, the meter, and the practical representations of the electrical units to take advantage of atomic and quantum phenomena to achieve levels of accuracy for realizing the respective units limited only by our technical capability and not by the definitions themselves. These advances in science, together with developments in measurement technology, have enabled changes to the SI, which have been promoted and explained in the previous editions of this brochure. This 9th edition of the SI brochure has been prepared following the adoption by the 26th meeting of the CGPM of a set of far-reaching changes. The meeting introduced a new approach by articulating the definitions of the units in general, and of the 7 base units in particular by fixing the numerical values of 7 defining constants. Among them are fundamental constants of nature, such as the Planck constant and the speed of light, so that the definitions are based on and represent our present understanding of the laws of physics. For the first time, a complete set of definitions is available that does not make reference to any artifact standards, material properties, or measurement descriptions. These changes enable the realizations of all units with an accuracy that is ultimately limited only by the quantum structure of nature and our technical abilities, but not by the definitions themselves. Any valid equation of physics relating the defining constants to a unit can be used to realize the unit, thus creating opportunities for innovation, realization everywhere with increasing accuracy as technology proceeds. Thus, this redefinition marks a significant and historic step forward. The changes were agreed by the CGPM in November 2018, with effect from May 20th, 2018, a date chosen because it is World Metrology Day, the day when the Meter Convention was signed in 1875. While the future impact of the changes will be far-reaching, great attention has been paid to ensure that these definitions are consistent with those in place at the time that the change was implemented. Editor's note: this 9th CGPM in 1948 initiated the study that led to the formal establishment of the SI by the 11th CGPM in 1960. We draw attention to the fact that since its establishment in 1960, the International System of Units has always been referred to as the SI in its shortened form. This principle has been maintained in the 8 previous editions of this brochure and was reaffirmed in Resolution 1 adopted at the 26th meeting of the CGPM, which also confirmed that the title of this brochure is simply the International System of Units. This consistency of reference to the SI reflects the efforts of the CGPM and the CIPM to ensure the continuity of the values and measurements expressed in SI units through each change that has been made. The text of this brochure has been prepared in order to provide a full description of the SI and to provide some historical background. It also has 4 appendices. Appendix 1 reproduces in chronological order all of the decisions, resolutions, recommendations, declarations promulgated since 1889 by the CGPM and the CIPM on units of measurement in the International System of Units. Appendix 2 is only available in an electronic version at www.bipm.org. It outlines the practical realization of the 7 base units and other important units in each field. This appendix will be updated regularly to reflect improvements in the experimental techniques available for realizing the units. Appendix 3 is only available in an electronic version at www.bipm.org. It discusses the units for photochemical and photobiological quantities. Appendix 4 provides some notes on the history of the development of the SI. We conclude by expressing our thanks to the members of the Comité Consultative des Unités of the CIPM, the CCU, known in English as the Consultative Committee for Units, who were responsible for drafting this brochure. Both the CCU and the CIPM have approved the final text. March 2019, B. Inglis, President CIPM, J. Ulrich, President CCU, MJT Milton, Director BIPM. Note on the text, the 22nd meeting that the CGPM decided in 2003 following a decision of the CIPM. In 1997, the symbol for the decimal marker shall either be the point on the line or the comma on the line. Following this decision and following custom in the 2 languages, in this edition, the point on the line is used as a decimal marker in the English text, and a comma on the line is used in the French text. This has no implication for the translation of the decimal marker into other languages. Small spelling variations occur in the language of the English-speaking countries, for instance, meter and meter, liter and liter. In this respect, the English text presented here follows the ISO IEC 80,000 series quantities and units. However, the symbols for SI units used in this brochure are the same in all languages. We should note that the official record of the meetings of the CGPM and the sessions of the CIPM is that of the French text. This brochure provides the text in English, but when an authoritative reference is required or when there is doubt about the interpretation of the text, the French should be used. Editors note the spelling of the English words is in accordance with the United States government printing office style manual, which follows from Webster's Third International Dictionary rather than the Oxford Dictionary. This page intentionally left blank. Introduction, the SI and the defining constants. This brochure presents information on the definition and use of the International System of Units, universally known as the SI from the French Système International des Unités. For it's the General Conference on Weights and Measures, CGPM has responsibility. In 1960, the 11th CGPM formally defined and established the SI and has subsequently revised it from time to time in response to the requirements of users and advances in science and technology. The most recent and perhaps the most significant revision of the SI since its establishment was made by the 26th CGPM 2018 and is documented in the 9th edition of the SI brochure. The Meter Convention, the CGPM, the Comité International des Poids Measures, CIPM, the Bureau International des Poids Measures, BIPM, the consultative committees are described in the text of the BIPM and the Meter Convention on page V. The SI is a consistent system of units were used in all aspects of life, including international trade, manufacturing, security, health and safety, protection of the environment, and the basic science that underpins all of these. A system of quantities underlying the SI and the equations relating them are based on the present description of nature and are familiar to all scientists, technologists, and engineers. The definitions of the SI units are established in terms of a set of 7 defining constants. A complete set of units can be derived from the fixed values of these defining constants expressed in the units of the SI. These 7 defining constants are the most fundamental feature of the definition of the entire system of units. These particular constants were chosen after having been identified as being the best choice, taking into account the previous definition of the SI, which are based on 7 base units and progress in science. A variety of experimental methods described by the CIPM consultative committees may be used to realize the definitions. Descriptions of these realizations are also referred to as basis and critique. Realizations may be revised whenever new experiments are developed. For this reason, advice on realizing the definitions is not included in this brochure, but is available on the BIPM website. 1.2. Motivation for the use of defining constants to define the SI. Historically, SI units have been presented in terms of a set of, most recently, 7 base units. All other units described as derived units are constructed as products of powers of the base units. Different types of definitions of the base units have been used. Specific properties of artifacts such as the mass of the international prototype, IPK, for the unit kilogram, a specific physical state such as the triple point of water for the unit Kelvin, idealized experimental prescription. Editor's note, this sentence has been modified for clarity. This sentence right here. Different types of definitions of the base units have been used. Specific properties of artifacts, such as the mass of the international prototype, IPK for the unit kilogram, a specific physical state, such as the triple point of water for the unit Kelvin, idealized experimental prescriptions, as in the case of the ampere and the candela, or constants of nature, such as the speed of light for the definition of the unit meter. To be of any practical use, these units not only have to be defined, but they also have to be realized physically for dissemination. In the case of an artifact, the definition and the realization are equivalent, a path that was pursued by advanced ancient civilizations. Although this is simple and clear, artifacts involve the risk of loss, damage, or change. Other types of unit definitions are increasingly abstract or idealized. Here, the realizations are separated conceptually from the definitions, so that the units can, as a matter of principle, be realized independently at any place and at any time. In addition, new and superior realizations may be introduced as science and technologies develop without the need to redefine the unit. These advantages most obviously seen with the history of the definition of the meter from artifacts through an atomic reference transition to the fixed numerical value of the speed of light led to the decision to define all units by using defining constants. The choice of the base units was never unique, but grew historically and became familiar to users of the SI. This description in terms of base and derived units is maintained in the present definition of the SI, but has been reformulated as a consequence of adoption of the defining constants. 1.3 Implementation of the SI. The definitions of the SI units as decided by the CGPM represents the highest reference level for measurement traceability to the SI. Metrology institutes around the world establish the practical realizations of the definitions in order to allow for traceability of measurements to the SI. The consultative committees provide the framework for establishing the equivalence of the realizations in order to harmonize traceability worldwide. Standardization bodies may specify further details or quantities in units and rules for their application where these are needed by interested parties. Whenever SI units are involved, these standards must refer to the definitions by the CGPM. Many such specifications are listed, for example, in the standards developed by the International Organization for Standardization and the International Electrotechnical Commission, IEC 80,000 series of international standards. Individual countries have established rules concerning the use of units by national legislation, either for general use or for specific areas such as commerce, health, public safety, and education. In almost all countries, this legislation is based on the SI. The International Organization of Legal Metrology, OIML, is charged with the international harmonization of the technical specifications of this legislation. 2. The International System of Units. 2.1 Defining the unit of a quantity. The value of a quantity is generally expressed as the product of a number and a unit. The unit is simply a particular example of the quantity concerned, which is used as a reference, and the number is the ratio of the value of the quantity to the unit. For a particular quantity, different units may be used. For example, the value of the speed v of a particle may be expressed as v equals 25 meters per second, or v equals 90 kilometers per hour, or meter per second and kilometer per hour are alternative units for the same value of the quantity speed. For example, the speed of light in vacuum is a constant of nature denoted by c, whose value in SI units is given by the relation c equals 299,792,458 meters per second, where the numerical value is 299,792,458 and the unit is meters per second. Before stating the result of a measurement, it is essential that the quantity being presented is adequately described. This may be simple, as in the case of the length of a particular steel rod, but can become more complex when higher accuracy is required and where additional parameters such as temperature need to be specified. When a measurement result of a quantity is reported, the estimated value of the measure and the quantity to be measured and the uncertainty associated with that value are necessary. Both are expressed in the same unit. Definition of the SI 2.2. As for any quantity, the value of a fundamental constant can be expressed as the product of a number and a unit. The definitions below specify the exact numerical value of each constant when its value is expressed in the corresponding SI unit. By fixing the exact numerical value, the unit becomes defined, since the product of the numerical value and the unit has to equal the value of the constant, which is postulated to be invariant. The 7 constants are chosen in such a way that any unit of the SI can be written either through a defining constant itself or through products or quotients of defining constants. Quotients of SI units may be expressed using either a solidus or a negative exponent. For example, meters per second equals meters seconds to the negative 1 power. Mole divided by mole equals mole times mole to the negative 1 power. The International System of Units, the SI, is a system of units in which the unperturbed ground state hyperfine transition frequency of the cesium-133 atom is 9,192,631,770 Hz. The speed of light in vacuum, c, is 299,792,458 meters per second. The Planck constant, h, is 6.62607015 times 10 to the negative 34 joule seconds. The elementary charge E is 1.602176634 times 10 to the negative 19 coulombs. The Boltzmann constant K is 1.380649 times 10 to the negative 23rd joules per Kelvin. The Avogadro constant N sub A is capital N sub capital A is 6.022140076 times 10 to the 23rd moles to the negative 1 power. The luminous
efficacy of monochromatic radiation of frequency 540 times 10 to the 12th hertz. Capital K sub CD is 683 lumens per watt, where the hertz, joule, coulomb, lumen, and watt with unit symbols HC, J, C, LM, and W respectively are related to the units second, meter, kilogram, ampere, Kelvin, mole, and candela with unit symbols S, lowercase s, lowercase m, lowercase kg, capital A, capital K, lowercase mol, and lowercase cd respectively. According to hertz is inverse second, joule is kilogram, meter squared, inverse second squared, C is coulombs is ampere seconds, lumens is candela meters squared, inverse meters squared equals candela steradian, watts equals kilogram, meters squared, inverse second cubed. The numerical values of the 7 defining constants have no uncertainty. Table 1, the 7 defining constants of the SI and the 7 corresponding units they define. Here's the table. It's basically the same information as presented here, but in a table format. Preserving continuity as far as possible has always been an essential feature of any changes to the international system of units. The numerical values of the defining constants have been chosen to be consistent with the earlier definitions insofar as advances in science and knowledge allow. Okay, I'm going to pause.